Some important compounds of boron are borax, orthoboric acid, and diborane. We will discuss each of them in turn. Borax is the most important boron compound. Borax is used as a flux in soldering and as a cleaning agent in leather industry and laundry. Found as a white crystalline solid, as shown in the photograph, borax is a decahydrate of sodium tetraborate that you see here. Borax actually contains the hydroxyborate ion tetranuclear units, illustrated here. Hence, the correct formula for borax is Na2B4O5 OH taken 4 times, 8H2O. Borax dissolves in water and the resulting solution is alkaline. As shown in the reaction, when borax is placed in water, sodium hydroxide is produced. When borax is heated, it loses its water of crystallization and swells. The resulting white, opaque mass is anhydrous sodium tetraborate. When the anhydrous sodium tetraborate is further heated, it becomes a transparent liquid. When solidified, this is referred to as borax bead, which contains sodium metaborate NaBO2 and boric anhydride B2O3. The borax bead test is a qualitative way to test for the presence of transition metal ions. A platinum loop is used to heat a small sample of borax in a Bunsen burner flame until a borax bead forms. The bead is then dipped into a small sample of the substance being tested. Then, it is held in the lower part of the flame, allowed to cool, and then heated in the upper or oxidizing part of the flame. The formation of a colored metaborates of transition metals identifies the presence of transition metal ions. For example, cobalt ions give a blue-colored bead in this test. Orthoboric acid is another important compound of boron. Its chemical formula is H3BO3. It is also a white, crystalline solid. Orthoboric acid is only sparingly soluble in cool water, but highly soluble in hot water. Orthoboric acid forms a layered structure. The molecules of orthoboric acid, which can be written as BOH, taken thrice, arrange in a plane, and the molecules link together by hydrogen bonds. Try to answer this question independently before proceeding. Why is orthoboric acid a weak acid? Answer. One definition of an acid is its ability to release hydrogen ions. Orthoboric acid is not a protonic acid and doesn't release hydrogen ions on its own. It acts as a weak loose acid. As shown in the reaction, it can accept an electron pair from water to complete its own octet, thereby releasing the hydronium ion. Since it is a weak acid, the Ka value of orthoboric acid is very low, of the order of 10 to the power minus 10. There are mainly two ways to prepare orthoboric acid. One way is to acidify an aqueous solution of borax. The balanced equation is given here. Another way to prepare orthoboric acid is the hydrolysis of boron compounds. For example, the reaction of boron trifluoride with water yields fluoroboric acid, HbF4, along with orthoboric acid. When heated above 370 Kelvin, orthoboric acid decomposes to form metaboric acid, HBO2. If metaboric acid is heated further, it will form boric oxide, B2O3. Diborane, B2H6, whose structure is illustrated here, is another important compound of boron. Boranes are a class of compounds containing only boron and hydrogen. Diborane is a colorless, highly toxic and extremely reactive. This colorless and highly toxic gas has a boiling point of 180 Kelvin. There are several ways to prepare diborane. One route involves reacting boron trifluoride with lithium aluminium hydride in presence of diethyl ether, as shown by this chemical equation. In the laboratory, oxidization of sodium borohydride with iodine produces diborane. Sodium iodide and hydrogen gas are the byproducts of this reaction. Try to answer this question on your own before continuing. Identify the oxidizing agent and the reducing agent in the reaction of sodium borohydride with iodine. Recall that an oxidizing agent is a substance that gets reduced. I2, which has an oxidation state of 0, forms an iodide ion with an oxidation number of -1. Since iodine is reduced, it must be the oxidizing agent. Therefore, NaBH4 must be the reducing agent. The third method for preparing diborane on an industrial scale involves the reaction of boron trifluoride with sodium hydride at 450 Kelvin. Sodium fluoride is the other product of the reaction. In air, diborane catches fire spontaneously. The reaction of diborane and oxygen is extremely exothermic, releasing 1976 kilojoules of energy for each mole of diborane. Boranes were once considered for use as solid fuels for rockets because of their exothermic reaction with oxygen. When placed in water, diborane undergoes hydrolysis to form orthoboric acid, as shown in the reaction here. Hydrogen gas is also released in this reaction. Diborane undergoes cleavage reactions with Lewis bases. In these reactions, the diborane molecule breaks apart to form borane adducts with the Lewis base. Two examples of these cleavage reactions are shown. One with trimethylamine and the other with carbon monoxide. Diborane can react with ammonia. Initially, the reaction of diborane with ammonia produces an adduct diammoniate of diborane. This exists in a slightly different form, as shown in the chemical equation. When this substance is heated further, borazine, B3N3H6 is formed. Note the alternating boron and nitrogen atoms in the 6-membered ring of borazine. Since it resembles structurally with benzene, it is called as inorganic benzene. Diborane is an electron-deficient molecule. Notice the peculiar structure of it. The 2 boron atoms and the 4 terminal hydrogen atoms of the molecule are all in the same plane. These 4 terminal BH bonds are regular 2-centered 2-electron bonds. The bridging hydrogen atoms lie above and below this plane. The 2 bridge BHB bonds are unusual 3-centered 2-electron bonds. The bond lengths are different as well. The bond length of the bridging hydrogen and boron is 134 picometers in length, while the bond length of the terminal hydrogens and boron is only 119 picometers. The boron atoms in diborane undergo sp3 hybridization. The overlapping of a vacant sp3 hybrid orbital of one boron atom and sp3 hybrid orbital of another boron atom containing one electron with the pure s orbital of bridging hydrogens containing one electron results in the banana bonds. Similarly, other banana bond is formed on other side. Thus, the 2 banana bonds formed lie above and below the plane of the boron atoms. The remaining 2 sp3 hybrid orbitals of each boron atom overlap with terminal hydrogen atoms to form normal sigma bonds. This results in the formation of 4 terminal hydrogen bonds. Boron forms a series of hybridoborates. One such ion is the borohydride ion, BH4-, which has a tetrahedral geometry. Sodium borohydride and lithium borohydride can be prepared by reacting the metal hydride with diborane, as shown in the equation here. Borohydrides are good reducing agents. Thus, they are widely used in organic synthesis, as well as to prepare other metal borohydrides. Boron has a number of applications. Because it is a hard solid with a high melting point, low density, and low electrical conductivity. Boron fibers are used to make bulletproof vests and light-weighted composite material for aeroplanes. The boron-10 isotope has a high ability to absorb neutrons. Therefore, metal borides are used as control rods and protective shields in nuclear power plants. Borax and boric acid are used in the manufacture of heat-resistant glass, such as Pyrex. They are also used to make glass wool and fiberglass. Borax is used as a flux for soldering metals, for heat, scratch, and stain-resistant glazed coatings for ceramics, and in the manufacture of medicinal soaps. Dilute aqueous solutions of boric acid can be used as mild antiseptics as well as an eye wash. Let's turn our attention to the properties of aluminium. Aluminium is a bright silvery white metal. It has a high tensile strength. It also has high thermal and electrical conductivity. In fact, its electrical conductivity is twice that of copper. when compared on mass to mass basis. Aluminium forms a number of alloys with various elements, including copper, manganese, magnesium, silicon, and zinc. Aluminium and its alloys are readily shaped into pipes, tubing, rods, wires, or foils. Hence, aluminium and its alloys are widely used in packing, cookware, utensil making, construction, aeroplanes, and transportation industry. Recycling of aluminium is significantly less expensive than mining and refining aluminium ore. It's better for the environment too. So always recycle your aluminium cans.